Hi AP Physics, it's Mr. Neff. Today we're going to talk interference and superposition. I have a joke for you today. Why do physics teachers make good dancers? I'll tell you at the end of the video. All waves do four predictable things. They interfere, they diffract, they reflect, and they refract. Interference is what we're going to talk about here today. Interference is whenever two waves are trying to occupy the same space in the same medium. And what it ends up happening is the two waves add together, have their amplitudes add together, and they give you a combination wave of the two. The other ones will be covered in other videos. So as I said, when waves interfere, they try to occupy the same space, and they form what we call an interference pattern, which you can very, very easily come up with mathematically. I found this nifty simulator from our friends over at zonalendeducation.com. And this is a neat thing. They have two waves here. They have a wave that is a rectangular and a wave that is elliptical on the amplitudes. And if I take these two and I overlap them, that is, try to make them occupy the same space, you can see what happens. I get what we call an interference pattern. The white one on the screen is an interference pattern. The interference pattern is just simply the arithmetic sum of the two waves' amplitudes. So that is, I'm going to add a particular spot, maybe right here, I'm going to add the amplitude of the red one, which would be about this big, and the amplitude of the blue one, which would be bigger, and the spot on the interference pattern is as big as those two amplitudes added together. And so that's where you can see that it just looks like the red one is stacked on top of the blue one, because it really is. Now, normally, all you get to see is the medium, not the individual waves. So when we're looking at this simulator, we're sort of cheating. And so I'm going to take away wave 1, I'm going to take away wave 2, and now you just see the interference pattern. So this would be, maybe you could just see the surface of the water or the string that these are moving through. And so you see the places where they're interfering, we have our constructive interference, meaning that the wave that is being produced is a much larger wave than each one of the two. You know it's constructive interference whenever the two amplitudes were in the same direction, and so you're adding together rather than subtracting off. Depending on what the shapes of the waves are, you can get a lot of pretty neat patterns. Here's a triangle added onto a triangle. You can see that a triangle added onto a triangle gives you this basically horizontal line, kind of a neat thing. There you go. And you'll be able to link to this simulator in the comment section below, and so you can check this thing out for yourself. Now I also wanted to show you another one that they have, and this is neat. This lets you add two sine waves together. And you can see that sometimes the sine waves are going to be lined up so that, well, the red one's trying to move the medium up and the blue one's trying to move the medium down, which is giving us nothing. We call this destructive interference. Destructive interference is any time the two amplitudes are in opposite directions. That is, the two waves are trying to move the medium in opposite directions. And it's going to give you a small wave. Now, in a situation like this, we call it total destructive interference because we have exactly opposite amplitudes, and we will get exactly zero from it. At the same time, we can move over half a step, and this is important for us, especially for the example at the end of the video. You can see that here we are with total destructive interference, but then if we just move a quarter of a period, now you see that we get very much constructive interference. They're lined up what we would call in phase, crest on crest, and we get this big super wave, versus whenever they're lined up out of phase, that is crest on trough, we get destructive interference, and in this case total destructive interference, we're getting nothing. That idea that I just explained is called linear superposition. Linear superposition is saying that all you have to do to get the interference pattern is add the two magnitudes together. Sometimes you'll get the waves lining up so that you get a larger wave, and we call that constructive interference. You see, these two waves are in phase. In phase? Yes, in phase. This trough and this trough are lined up on top of each other, and look down in the interference pattern, we're getting a super trough. At the same time, we have a crest lining up on a crest, and look down in the interference pattern, we're getting a supercrest. Constructive interference whenever they are lined up in phase, whenever I have a positive amplitude adding on to a positive amplitude, or a negative amplitude adding on to a negative amplitude, both examples of constructive interference. Over on this other side, we have destructive interference. Now you can see that these two waves are lined up out of phase. I've got trough lining up on crest, and you can see down in the interference pattern, I'm adding a positive number to its negative number, and I'm getting 0. And over here, I have a crest lining up on a trough, and you can see again that I'm getting a 0. It doesn't always have to give you this total flat line like this. This is total destructive interference. You could just get something smaller, and that would be destructive interference as well. Here's a nice example for us, and it shows us that we have 2 square wave pulses. And so these 2 pulses are traveling at each other, and they're moving at the same speed. They're in the same medium, so they will be moving at the same speed. All waves always show that. And they are moving at a constant speed of 1 centimeter per second. And here is where they are at time equals 0. And so they ask you to show what would the interference pattern look like 1 second, 2 seconds, 3 seconds, and 4 seconds later. Look at the wave on the left. It right now goes from a position of 3 to a position of 5. And the wave on the right goes from a position of 7 to a position of 9. They're both going to move 1 centimeter forward. So instead of 3 to 5 for the left one, it's going to be 4 to 6. And instead of 7 to 9 for the right one, it's going to be 6 to 8. And so I'm going to have from 4 all the way out to 8, I'm going to have wave. Now it looks like one wave, and it is one interference pattern. It is really the wave on the left occupying the 4 to 6 spot, and the wave on the right occupying the 6 to 8 spot. Now, if we move them both forward one more unit, instead of 4 to 6 for the left, it'll be 5 to 7, and instead of 6 to 8 for the right, it will be 5 to 7. And so the wave's actually going to be 2 units tall right there and 0 units tall everywhere else. And now if we just continue the trend, the one on the left will continue to move to the right, and it will now be in the space that's 6 to 8, and the one on the right will continue to move to the left, and it'll now be in the spot that's 4 to 6. And so we're going to get a picture that looks identical to the one we started with, and then we're going to get a picture, get my picture out of the way there, then we're going to get a picture that looks like the one that we started with, and it's going to go 3 to 5 and 7 to 9. There we are. This last example is a little bit more challenging, but it is a neat thing and a neat example of interference that everyone can relate to. Here we have 2 speakers, and they're playing an identical 125 hertz tone, which we're going to see later on is a pretty low sound. The speakers are 5 meters apart, and we have an observer down here at 90 degrees. Now, they want us to figure out the distance, the farthest distance that he could possibly be, and we can still get destructive interference. Now there's a lot going on here, and so let's talk. For him to get destructive interference, that means the 2 waves have to be arriving out of phase. And so maybe if I draw the sound waves here, I'll just draw some compressions. Remember, sound waves are longitudinal, and so they have this compression. And so there's one right there. Let's say that one hits him in the ear. Now, the other wave, I'll just draw it in a different color just so we can tell the 2 apart. I'm trying my best to draw these equal wavelengths. And so you can see let me draw one more black one there. This actually did work out very, very well for me. Right there at his ear, we've got a spot where we're between waves on the black one, and we're on a wave compression on the red one. That's a place where the two waves are out of phase. And so right there, it's going to sound quiet. The places where we have two compressions overlapping, or in a place where we have two rarefactions overlapping, that's where it's going to sound loud because we're going to get destructive or constructive interference. We want a place where it's going to sound quiet and we're going to get destructive interference. Now, for this to happen, this path length, we'll call this path length 1. And this path length, we'll call this path length 2. They have to be different by half of a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength. So we'll get them arriving on compression and rarefaction. We'll get them arriving out of phase. So all that is to say that if I did path length 1 minus path length 2, I'll do 1 first because it's longer. I either have to get half of a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, or so on and so forth, like this. Any of those would do to give destructive interference. Well, if you think about it, imagine if he was very, very close. If he was very, very close, the triangle that's formed by the two speakers in his ear, well, it looks sort of like that. Now, if he moves farther away, the distance between the speakers stays the same, but this leg BC, keeps getting longer and longer. Now, in this first picture, there's a huge difference between this hypotenuse and this leg. But in this picture, there's less of a difference between this hypotenuse and this leg. And as we keep this side the same, but keep making this leg longer and longer, eventually we start to get not nearly as much difference between those two. And eventually we'll say that if we make this any farther, then the difference between them will be very small, and most importantly here, it will not be half of a wavelength. So all that is to say that if he's going to indeed have this destructive interference, that path length 1 minus path length 2 has to be equal to half of a wavelength. Okay? So now, how long is a wavelength here? Well, you can see that they gave us the wave speed and they gave us the frequency. So getting the wavelength is going to be a pretty simple thing. Wave speed is wavelength times frequency. So wavelength is wave speed divided by frequency. And if you substitute in there, you'll get a wavelength of 2.744 meters. That's what one full wavelength is. I'd like to know what half of a wavelength is. It's as simple as dividing that by 2. And we'll say that half of a wavelength is 1.372 meters. Now, we'll say if the path length between the two is 1.372 meters, well, that says that this side A and this side B and this side C, we know they're related with Pythagorean theorem, a squared plus b squared equals c squared. And so I'll say that this is 5 as given in the problem. I'll say that this b is, well, the answer, let's make it x, and let's say c is x plus 1.372. If you go ahead and solve that quadratic, you're going to get a length of 8.42 meters. So if he's any farther than 8.42 meters, he'll never be able to get the two path lengths to be half a wavelength apart. I hope you enjoyed the video today. And why are physics teachers good dancers? Because they've got algorithm.